All right, welcome back, everybody. We're starting the next phase here of our journey. We're going to start transitioning into manipulation in Clutter, and I'll tell you the implications of that in the next slide. Quick admin announcements. So we're getting closer to where we're going to start defining projects, and you'll have a project pre-proposal first, where some people submit the pre-proposal, get a rubber stamp, and then they're good. But the pre-proposal is a chance, if you haven't already, to give us a draft of what you're thinking and get some feedback before we lock it in with a more final proposal. So that the first pre-proposal is due on October 20th, which seems like infinitely far away, but it'll be here before you know it. So start thinking about who your project groups are. If you're in CIM and you look around your CIM recitation, that's the ideal setting for all the CIM content. To have a group inside one recitation is ideal. Not required, but ideal. And if you want feedback from us beforehand, some of you have been coming up and asking after class, which is great. Sometimes, actually today is the one day I have to leave like right after class, but almost always I'm here after class, and then just a second, and then or even I'll come early before class if you want to talk, or send me an email, or send the staff an email. This is a good time to be just throwing ideas off us. No, it definitely does not need to be a novel. The rubrics for the project are on the website. As we get a little bit closer still, I'll go over that. But absolutely, like finding a paper and reproducing it and understanding it is great. Yeah. But the partnering was we wanted to at least put in your head. Yes?
Quickly, just a question. What's like the size of your group?
Yeah, so 1 is fine. You can work by yourself. That's great. 2 or 3 is great. I think more than 3 starts to get harder. So we normally say 2 or 3 is ideal for a group. Great, and you've already been looking a little bit at the projects from last year, so you have a sense, but you're not gonna feel restricted to robots on a table this year, because we're gonna have a lecture right before your pre-proposals are due with mobile robots doing all kinds of stuff. Okay, assuming I can get mobile robots to do all kinds of stuff in simulation in time, hopefully. Okay. So let me just sort of step back for a second and just think about what have we done so far, and why are we going to do this next? Remember, I tried to tell you that I've tried to organize the course sort of in, we basically now have established a very basic capability, and now we're going to try to address the things that were limitations of our previous approaches. So we started with a quick lecture on hardware basics, just to help you appreciate what we're commanding and controlling. And then we talked about the basic pick and place, where we assumed the known pose was given to us, and we assumed we knew the object because we had to pick the grasp relative to the object model, right? And then we were able to do kinematics and Jacobian-based control to do a full manipulation task, but with some big assumptions. And then last week, we talked about geometric perception, which was the entry-level perception, which if you have a model of the mustard bottle, for instance, and you see a mustard bottle in the world, we can use ICP and the variance and some of the important variants to try to estimate the pose. So that removed the biggest assumption, I would say, of assuming someone knew a priori where the pose was, and we brought in a little bit of perception. But that pipeline was still assuming a lot, right? So in particular, the known object appears a lot there. We assumed we knew the objects. We want to do more complex scenes with many objects and more diverse objects, where potentially you don't even have a chance of knowing a perfect model of the object we're manipulating. And that's going to change the requirements on both the control and planning stack and the perception stack. But to start into that, we can still sort of just say we're going to do a basic sort of pick and place kind of operation. I want you to think by the end of the course of manipulation as way more than pick and place. Right? We do, like, tying shoelaces, I think, is a better example of what manipulation is than pick and place, even though a lot of robots do pick and place. So as kind of a way to structure that, our next sort of task is based around this idea of building a little clutter clearing station. Okay, so we did this in the early days of the manipulation team at TRI, and the reason for it was because this was just at the dawn of deep learning solving a lot of computer vision problems. And still today, but today we're more often using pre-trained models than back then. Okay, we really needed to generate a lot of data and a lot of diverse data of the robot's hands around novel objects in both sim and in real. So we just devised this very simple, and other people have definitely done this too, simple setup where you have two bins, and their job is just to pick all the stuff from the one bin and drop it in the other bin. Okay, but we assume nothing about the objects in there, and in general, we just threw whatever objects we wanted into the bin, and we got a lot of diversity from that. If you watch this closely enough, you'll see it's mostly pick and place, but this system got to the point where we could do some more subtle things, like I bet, okay, there's a banana still, but I bet to get the pillbox out of the corner, it's gonna like go in and do, it can't grasp that probably in first shot. I think it just ended. Was I really, am I that unlucky? Like the whole video was playing for like a minute and a half, and then as soon as I say something, it stops. Yeah.
Yeah, in the first round, when it was first moving,
Yeah. So yeah, okay, if it's possible that it missed that one, yeah, or that it was occluded or something like that. Yeah. Good eye though. He says it didn't move the pill bottle, so it skipped it. There's a little rubber duck that has looks like Spock from Star Trek. And I don't know, it always ended up on the floor. I don't know, there was no, it was just supposed to do this, but it seemed like with high probability, it would throw Spock onto the floor. It must have been something about the geometry or the compliance or something, but I thought it was hilarious, yeah. Okay, so of course we can do this in simulation too. So this is my little, let's see, look at that, I'm having started it not from the beginning here. Okay, so we're just gonna start with random objects. These are familiar objects if you've played with the YCB object data set. Okay, they all have ridiculously big mesh texture files. Okay, but cameras just like we set up before, but now we have random objects, and we're gonna sit there and build not only the bits we've done before, but we're gonna generalize our perception system. We're gonna talk about the more complicated simulation that happens here, and we're gonna have to build a higher level state machine to think about the logic of, okay, I missed something. Let's gonna go back and try to pick something up again. So it brings up a little bit of some of the task planning too. Okay. So the first question you get if you're trying to, in simulation, and you sort of saw it at the beginning of my animation, but the first question is, how do you generate diverse random simulations? Okay, and the problem in its full glory is actually fairly hard. But if you're willing, in this sort of clutter clearing setup, and actually in a lot of robot experiments, people that were have been training deep learning perception system from simulated images and the like, it's a fairly common workflow to generate random environments by basically dropping things out of the sky. Okay, so if you want to come up with a distribution, a random distribution of clutter, this is like a pretty good way to do it, right? And it's it's for a few subtle reasons. Okay, one of them is that so basically, this is relying on the physics engine to come up with the, you give it random initial conditions, but the physics engine is really finding the static equilibrium of postures for you. Okay, and physics is a powerful thing, and it's well defined almost always, except for when objects are in deep penetration, right? So if I were to just start the physics engine with all of the objects completely on top of each other at 0, 0, 0, then I don't know what it would do, but probably things would be flying off in different directions because of numerical instabilities. Because really the context solvers shouldn't be asked to solve that problem. That shouldn't happen in reality. Okay, so a common heuristic is so you'd like to start objects out of penetration, and that's sort of hard in this, like if I had to pick configurations here that had to be all out of penetration, that would be that's a puzzle to solve, right? And we can do that with optimization. If I have time, I'll talk about that. But it's just much easier. The script here is very simple. You basically pick, this is just all foam bricks, but I'll show you it works more generally. Pick an object, go up a little bit from the bin, pick a random translation, a random pose, okay? and then lock that one in. Now go up a little bit higher so that you're pretty confident that you're not in an intersection. Pick a random position and random pose, okay? And you just make a stack that is safely out of collision, and then you let physics do the work, okay? Which in some ways is a really clever, like I say, physics is pretty good, right? I mean, like it's solving a really hard problem by solving governing equations, yeah? You can do that with arbitrary objects, of course. So this is the YCB objects, is this pretty famous, I mean, it's almost a folklore, thing where, so the Yale, Cal, Berkeley, there were investigators from all three schools that decided that we should make a common data set, we should just agree. They bought a bunch of objects on Amazon, they scanned them and offered the scans as part of their paper data set, and they said, here's the part numbers, you can, if you contact us, we'll give you those, a copy of those, or you can just order them online, right? And so we have this data set of people that, lots of people could work with the same objects. Super useful. It sucks that, now, like the packaging has changed, right? So you can't get that Cheez-It box. You can get one with like low sodium, and you can't, but it's still pretty good. It's still pretty good. So if you can like find a vintage Cheez-It box that matches the YCB, you could probably, get some money for that on eBay with the robotics market, Okay, but you'll see like a handful of these objects that I use over and over and over again because they're the canonical ones. And if you drop them out of the sky, you get things like this, and it just works fine, right? It's kind of, I always think it's funny, it's like the central limit theorem at work, even if it's like Spam cans and mustard bottles, right? But that's just uniform, that's a uniform sampler, and just, there you go, and you get these pileups. So that works fine. And of course, it works fine in 3D. So this is me dropping things out of the sky, putting in a camera right above, and generating a picture of the bin like the overhead camera would see. And when we get to some of the deep learning based perception, we'll use this as a data set. I just dropped it like 10,000 times and just made 10,000 images, and they're all labeled and just from random initial conditions. And that's a pretty good data set to train Cheez-It box detectors in Clutter. Okay, but so that's like very easy to say. You just run it in the physics engine, just drop your assets in. It's a few lines of code. But when I got to this part, I was like, okay, I have to tell you a little bit about context simulation, because there's so much behind that little, drop the spam can thing, right? There's so much smarts there. There's so much subtlety there. And some of it you'll need to know, like you'll find yourself in a situation where if you know this, you will persevere. If you don't know this, your objects will fall off the table or out of your hand or explode into space. So I want to spend a day talking a bit about context simulation, okay? And just maybe to make the point, I can even show the notebook here. So that's the 2D one, it works fine. Mix the video, here's the 3D one. It really is a few lines of code. I just, see if I can make that a little bigger here. Close that. Right, I just actually make this scenario file, and I just said for one in range 10, pick a random object and drop it into the file, and then load it, and we're good to go. And then we set a random initial position, and that's a few lines of code. Okay, and what you get out is the scene, but if you draw the contact force vectors, right, you realize that to find a static equilibrium of this system, the contact engine is actually doing a lot of work, right? It's solving for a lot of contact forces to find a static equilibrium, right? This is solving good physics problems. And so let's just dig a little bit into what that problem is that it's solving and some of the subtleties about how it solves it. Okay, so we talked already about spatial quantities. We talked about positions and poses and rotation matrices. We talked about spatial velocities. Today we need to add spatial force, right? So today we're going to start talking about forces, right? So what's a spatial force, right? Force is force, right? What's a spatial force? Okay, so a spatial force is a 6-dimensional quantity. Let me start with this, which has 3 components that you would sort of expect, but also has 3 components. This is the sort of translational, and this is a 3x1 rotational. So just like the spatial velocity vector has angular velocity and translational velocity, the forces have that too. We're going to annotate this the same way. Forces, we like to have names on their own, okay? But they're also, I'll label everything in a second here. So we write the expressed in frame down here. For consistency with the other notation, it's still expressed in. There's never a relative or measured in frame for forces. You don't need that. Forces are forces. And this is the point that the force is applied. Okay, we often name the point with the body name as well as the point name, just to remember that it's a force being applied, let's add on body B at point B. It's just a recommendation, sort of. Because you're going to find yourself with a point on body A that's coincident with a point on body B, and there's equal and opposite forces, and if you don't remember to sort of which one you're talking about, it gets confusing fast. Yeah?
How can there be a rotational force?
Yep, so good. So what the heck is a rotational force? Let me just finish writing it here. This is a torque, yes, that's why tau for torque. This is name C and BP. Okay, I've just written this a little wider. What's that? Yeah, this is an important spatial quantity. So we have an entire algebra. The question is why would you mix this up and put this together? You're going to see, I think, in a very simple example, maybe a compelling reason why to do it in just a second. But our entire spatial algebra is going to be defined really in these 6-dimensional spaces. Okay, so it made sense to do angular velocity as well as translational velocity. And it turns out, if you want to summarize, for instance, if the real world only applies Cartesian forces, right? Maybe you could say, I know it's just going to do it, I think. It's probably a weak connection. If the real world, you say, maybe only applies forces that are translational, then you still want to have the concept of a rotational force or torque if you want to summarize the translational force at a different point on the rigid body. Okay? So, and this spatial force is also known as wrench. You'll hear it called wrench commonly. Okay? I think I remembered to put yeah, okay. So instead of writing it all on the board, it's in the notes, and I'll just put it up on the screen. But basically, we have the same sort of algebra rules. Okay? So spatial forces add when they're applied to the same body in the same frame. Okay, so the only thing that's different here is the name of the force. Right? They're applied at the same, I should even say at the same point on the same body. Okay, in the same frame. Then you can add forces together. You can shift spatial forces to a different application point. Okay, it turns out for the translational force just shifts, but you start getting cross products, which you'll probably remember, R cross F kind of math from physics. You get cross products when you shift the point of application of a force. And we're going to see that in a second here. Okay. And then actually for basically all the spatial quantities, if you want to change that expressed in frame, you do that by multiplying by a rotation matrix. And that's it. And that's right in the notes. You can, okay, but we're going to use these in a second. So having this beautiful, algebra sort of concept, we can now do more complicated things in complicated systems by just applying these rules efficiently over and over again. So let's do that in a very, very simple example. Okay, so, whoops, forgot to erase that one. Although it looks pretty close to what I was going to write. Okay, so simple free body diagram. Okay, let's say I have a box sitting on a table. I should use multiple colors of chalk. I'll call this body B, and I'll put its frame here. And I'll even assume that the center of mass is right at the origin here. Okay, and I'm going to just set it on the table like this. And I'm going to think about, I'm going to start by summarizing the contact forces between the box and the table with two forces, one at each corner. We'll see if that's sufficient and talk about that in a minute, okay? But we'll call this contact force 1. So I'll call it F1, and it's going to be applied in a coordinate frame 1, okay? And it's applied at this point C1. Maybe I should call it BC1 and follow my own advice. Okay. It's a lot of symbols. It's a lot of symbols. I hate this one. I really don't like, but it really matters. Like otherwise, you're going to make them. In fact, when I was cleaning up the notes today, I found a mistake in one of my examples, and it's because I hadn't followed. I had tried to shortcut the notation, and I made a mistake. So we'll call this one force 2, okay, and apply it at coordinate frame C2. So I'm calling this a coordinate frame C2, okay. And then, of course, we have the force of gravity here, mg, which I'll call a force of gravity, okay. So let's just think about the statics problem here, static equilibrium. So when this is completely at rest, then we should be able to solve, knowing what we know about sort of forces and force balance, we should be able to solve for the contact forces here that would satisfy the fact that that block is not moving, right? Yeah. We're going to generalize this, okay, but so that's good. So let me assume it for now. But the one reason to assume it is that actually most simulators assume it. Most simulators, when they're trying to summarize the contact between two bodies, they will summarize that with a small number of points, okay? It'd be more elegant to have an entire pressure distribution. It just makes the math a little bit more complicated. And certainly this is sufficient to describe equilibrium. If I could put a little foot on the, on here, and then it would be real. You could make that physically true. Okay, so ask.
Why does this matter? Like when because this process, for example, at rest.
Yep.
Like it matters because in context like of the work on because then I can apply that like the opposite effect to be able to pick it up.
Good. So why does it matter? Yeah. So we are going to choose. So even to get ahead. So first of all, it gets a lot more complicated in this, right? So even just on the board in the previous slide, it's going to get a lot more complicated. Yeah. And so, for instance, one of the ways we're going to define a good good grasp is a grasp that can defy the maximal adversarial wrench. So if someone were to come up and try to apply a force or something, then you want to pick a grasp that tries to avoid the biggest possible wrench. And that would be a surrogate for not knowing very much about your object. So a good place to put your finger can be decided based on thinking about the relative force balances and things like that. That's a great question. Yes?
It's going back a bit from what we were saying, but is there a reason why both the simulation and the video is going to show up such low intensity?
They should go at real speed. You're saying that the blocks look like they fell slowly?
No, like the arm is moving.
Oh, I see. For the arm, yeah, that was just because I didn't we haven't done motion planning yet, basically. The diff IK thing, I was just being conservative and trying to make it move slowly and avoid cameras and stuff like that. But we're gonna have better tools, yes. And we'll just hopefully be whipping around and probably, throwing objects out of the hand and stuff like that. Last year also, if you noticed in the projects, there was a surprising number of people that wanted to throw or whip or crush or whatever things, which is cool. Yeah, I'm good with that. Someone says we're going to do darts and we want to do it on the real robot. I was like, whoa, let's not my real robot, But that can be a fun thing to do, and the robots are just capable. Like the Kuka is actually speed limited. It's not a super fast robot. That's not its finest attribute, but probably just enough if you put a little bit of a lever on the end to throw a dart. Yeah. But I don't support that for final projects. Okay. So let's start being a little bit more careful here. So F of gravity here, if I were to write it it's sort of best defined in the world frame, okay, and applied at the body frame here, where the center of mass is, because in that frame, it's easy to just say it's actually a 6-element vector, right, that has no torque. Right, this is my slightly more precise version of just writing negative mg there, okay? It's actually, in the spatial notation, it lives in a 6-dimensional space. The contact forces are actually most naturally described in the contact frame, which doesn't look very different than the body frame and the world frame in my first example, but it will look much different later examples, okay? So because it's most natural to say, for instance, that in this frame of contact, which will move with the possible contact locations, that, for instance, the force can never pull on the contact; it can only push, right? So, in the contact frame, by convention, the contact frame the z direction is aligned with the contact normal. So we have, for instance, that f of some I in the contact z applied to whatever body is going to be greater than or equal to 0, because you can't pull on, contacts push but don't pull. And I'm assuming that the ground is just locked in, it's not a body, but if it was 2 bodies colliding, then I would have a comparable contact frame on the other body, which this is also true, but it would be a different body, it would be a different frame, so equal and opposite frame. Yeah?
Because you're defining the contact point in the corner. And so the normal of the corner is the average of
Good.
the so like the thing that you showed here.
I'm going to tell you how to define the contact normal in a second. I've got a picture that will help with that. There's a general way to do that, but that's a great question. He says, you just said normal, but you put it in a place that has a corner, which the normal might be poorly defined, or you have to think about something more complicated in the corner, which is a good point. But there's a fairly clean way to define that. Okay, So then if we want to do our, our multi-body algorithms, it's a general multi-body algorithm or our basic free body diagram sort of computation, then we can just apply the rules of spatial algebra. And basically the step one would be, I'll do it over here. We're going to put all the forces in the same expressed in frame. I'll just do it in frame B, just to keep, I could pick any one of them. I could pick world, I could do anything, but let's do, okay, so for instance, I can just use that algebra and say force 1 written in body B, taken at point C1, that's a 1, is just rotated by the rotation from C1 to B of F1, C1, B, C1. Okay, I keep trying to make that an I, but it's not an I, it's a 1. And I could do the same thing for contact force 2, right? So what is that doing? That's just saying that there's a force here that I can express it in the frame of B. And the same way with positions and velocities, at the expressed in frame, I'm still applying it at this force. So if those two were not aligned, it would rotate the force, but it doesn't actually have a cross product or anything involved yet. The force is still being applied here. I'm just going to choose numbers that were relative to that coordinate system instead of this coordinate system. Okay? And then the second step would be to apply them all at the same point. Now that sounds totally weird, okay? Until you understand that for rigid bodies, if I were to apply a force here, that's indistinguishable from me applying a different force at any other point on the body, a force and a moment potentially at any other point in the body, right? So if you apply a force here, I could apply a different force and moment here that would have exactly the same effect. From the point of view of the rigid body, it's completely indistinguishable from applying this force I have here. So I'm going to use that, and that's what the rules of spatial algebra do, is they show you exactly how to do those transformations, okay? And I'm going to say, well, I'm going to take it as if I was pushing here. I'm going to make the comparable force and moment and torque here. And then same thing, this one, I'll move that to here too. And once they're in the same place, now everything has to balance, okay? They can add or subtract when they're in the same place. So this is where I get my translation. One is, it doesn't actually affect the translation one. C1, 1, P. But this is where the cross product comes in. So tau B1, B equals tau 1. I hate all the symbols, but it really does make a difference. That's a cross product, right? A vector cross product. These are both 3 by 3 vectors, and so that's a vector cross product. And this is just, in simpler free body diagrams, you probably would have just written this as R cross F, right? That's the standard. I'm producing a moment around the center of mass. Yes?
So you are producing, say there's no force and there's no moment. Does that equate equal to that after around which point you have the moment?
Nope. Nope. If you shift frames, then you are going to potentially make it look like a force again.
Yeah, but say if you're in the same frame. applied torque has different vectors. And surely that's not.
I see. You want the comparable thing. It's not that way. I mean, so applying the torque is almost a construction that makes sense for rigid bodies, right? As you said in the first thing, it's kind of three-dimensional forces are real. Torques are our summary of the effect of a body, so they do act a little differently. Yeah, they don't compose in the way I agree there could be a nice symmetry if that was true, but it's not. Yeah, they're different quantities. And then now we could solve for the contact forces if we like. That must be to put things in balance by just saying now that they're in the same frames, then F1B B plus F2 B B plus F. Actually, I could even do this in the big one all at once. I could do the components, or I could just do the whole thing. So big F gravity B, that has to equal 0 if I'm in equilibrium. It says I'm in static equilibrium. Okay, so that's 6 equations in its full glory. One for each row of those, right? In 2D, I guess you could say it's 3 equations because there's nothing out of plane that would make any difference. But in 3D, it's 6 equations. And so it's interesting, right? If you think about it and work it out, I won't write everything out on the board, but you can kind of guess what the solution is for that, right? So you'd probably think that this force had better have magnitude mg divided by 2. And this one had better be mg divided by 2, assuming this is nicely in the center. And that's what falls out of this. But you have to understand, actually, that the component that balances the z force, the z equation in this, that only tells me that the sum of those two vectors has to equal mg. It doesn't say anything about the relative magnitude of those two vectors. It's actually the torque balance, the fact that you have to have 0 net torque, the thing with the cross product, which says if that body's in the middle, then they will have equal magnitude. Okay? Yes?
It seems that we are assuming that all the contact forces here model is only like 1, 3, or 4. So that's also noted that there are something called like ordinal contact forces. And how does that work?
Yeah. So that's a good question. So some simulators, for instance, it's really kind of a simulator thing more than a math thing. Since point contacts are maybe a poor summary of a contact of face-on-face contact, some people will have the ability to produce frictional torque right at your point contact. Maybe that'll make more sense when I put the friction cone up in a second, because then we'll see it right there. But it's true that sometimes people model that. But that's really meant to model the effect of many forces in a patch. It's an approximation for that. Mm-hmm. Okay, so what about the horizontal components of the force? Oh, sorry, yes?
Yeah, and how is the force that is applied in our field? Do we just apply our force vertically, or do we calculate the global force that we apply to our center?
So you go through and you calculate all kinds of contacts that are potential contacts, and then in the rigid body algorithm that does this recursive step through, it summarizes things into a common frame and does all the algebra in the common frame and iterates through. So that's what makes things efficient and elegant. Yeah. So I'm only so far said what happens in equilibrium, and in that case, the forces are whatever they need to be to keep things at 0. Okay. We're going to see more complicated cases where maybe there is no force that can stabilize, for instance, and you have to make a choice. What's the force going to be? Yeah. For instance, already here we haven't said what the horizontal component of the force is. The force balance equations just tell me that that magnitude and that magnitude have to be equal so that it's not sliding. But any magnitude of any size as long as they're equal and opposite, would keep this block at rest. So we need some rule to say, like, what's the magnitude of that horizontal component. Yeah?
So in the example of like where you're dropping a bunch of objects,
Yeah.
are you just like iteratively like simulating the foreign objects and then settling into equilibrium, or are you like directly solving the static equilibrium?
So that was just simulating forward, and the simulation, because there's dissipation and physics is like clever, settles into a static equilibrium. Yeah. I mean, you have to be careful in your simulator to make sure that it's true, that everything converges nicely. But if you simulate the governing equations correctly, it should do that, as long as there's any dissipation. Yeah. Every once in a while, actually, if you watch the full simulation of the dropping the bin, I kind of was a little sloppy with the initial conditions. So sometimes it like the mustard will hit the edge of the bin and then fall like forever, because there's nothing else below. So it actually doesn't converge to an equilibrium because there's something falling to negative infinity. And at some point it'll crash, actually, which is, I don't like that it crashes, but don't simulate it for more than like 20 seconds if that happens. Okay. All right, so let's think about the horizontal component, because that gets us into friction. And this is really a fundamental concept that you must know if you're talking about manipulation, which is this concept of a friction cone. Okay, so maybe we'll see it by putting our box on a ramp now, okay? And now our contact, if I still have little feet on the corner here, I'll still call this C1, C2. I still have body 1 in the body frame here, okay? But now, if it's going to be in equilibrium, I have to do a little bit more work to make sure I've defined that horizontal component in the contact frame, right? And it turns out the most common model of friction is Coulomb friction, which says that the magnitude of the horizontal force is proportional to the magnitude of the normal force in the contact frame, right? So Coulomb friction if I can write it sort of in shorthand here first here. So this is the magnitude of the tangential component is proportional to the magnitude of the normal component. That's not using my whole notation yet. I'm going to make it in the proper frame in a second. Okay. But the normal, we say, is always positive. By our definition, that's our z component, okay? And so we're saying the xy component is actually, this is in the Euclidean norm, okay? Is proportional to this, and that proportion is called the friction coefficient. It's almost always mu. What? This is a scalar in this case. So this is the magnitude. So, yeah. That's why I wanted to use my whole thing. But in shorthand, if the magnitude of the normal, this is a vector, this is a scalar, actually. Yeah. So if I were to write it out, maybe it'll be more precise if I say of some thing in the contact z, that's definitely a scalar, applied, let's say, at body B, is actually going to be So in 2D, oh, sorry, I didn't see your hand. No. Yep. This is, so this is some sort of a norm when I put these up. And this just means it's the L2 norm, which means I want to take a square root. It's this thing squared. You can, the only other ones we'll ever use here, I probably can't even think of a time in this class where I use a different norm. Should I just never write that? Is that just confusing? But sometimes I would use a 1 for the L1 norm or an infinity for a infinity norm. Yep. But if you were to Google LP norm, for instance, that would tell you the story. Where P is 2. Okay, so the geometry of this thing is the geometry of a cone. Okay, so if I were to draw f of I cx, f of I cy, f of I cz here, then the elements of that three-dimensional vector that satisfy this constraint live inside a cone. It's like an ice cream cone to the origin. So when f of z is 0, these two must be 0, right? There's nothing below. It can't be negative. And as f of z gets bigger, I can have bigger resistive forces, which makes sense, right? If you push down on something and then try to slide it, it's going to be able to resist more than if you are gently touching something and try to slide it. Okay. It actually, it makes some of these statics problems very geometric, actually, and dynamics problems very geometric, because if you want to ask, for instance, is the box going to slide, or is it going to stick as a function of the ramp angle, then I'm going to draw it a little bigger here. So I've got a ramp, got a box. Okay, I've got friction cones now, which in 2D just look kind of like that, I guess. And I've got a force vector coming down. I'm going to use lots of colors today. And I've got a force coming down that's straight down. Okay? So it turns out, with our spatial algebra, or classic physics, but the spatial algebra just makes it neat, clear in my mind, we can move these forces as if they were being applied at the body location, right? And so they'll have some interpretation like this, and they'll add. So the condition, I got to finish my punchline. The condition here on, whether this thing has a force that's inside the friction cone that can resist motion is actually the geometric condition of whether the opposite force of that is inside the friction cone. Right? If there's a force that could be picked out of that cone, like any of these are possible admissible forces, if there's one that could be picked out of that cone, then there'll be an equilibrium. So in this case, maybe the way I drew it, it's like going to just a little bit slide, right? It's not quite enough. If I made the friction coefficient bigger, then I could resist that. If I made the normal force bigger, I could resist that, right? Or no, that's not true, because that would also increase this. If I made this thing larger, that's why it's geometric, and that's why it's beautiful, is that they would go up together. But or if I made the ramp smaller, then that could be inside there. Okay, so it becomes very geometric. Sorry, what was your question? Yep. So oftentimes, the normal force is determined first, and then that defines effectively the height of the cone. Not always. Typically, they're actually solved all jointly. Okay, but that's maybe the easiest way to think about it, is that the normal force determines the horizontal forces. Yeah.
So assuming that we have already obtained the unit vector for the normal, how does Drake or whatever calculate the tangential vector? Obviously, you can just any state that is of that effect.
So Good. So the laws of, so the question is, how do you actually pick one if maybe there's a set of possible choices? So typically there's not a set of possible choices because we have principles that tell us which one to pick. There's some caveats to that, okay? But the first thing is if the contact velocity, which is the velocity at the point of contact, is 0, or can be made 0, then the contact, the frictional force would be whatever causes the balance. I was thought about writing that out in symbols, but I decided this one I should just write in words because I wanted to find another frame for contact velocity and stuff like that. But tell me if that's clear, right? So if there's a sticking mode, okay, where if you're in sticking mode, it will choose the choice out of this necessary to satisfy the equilibrium conditions. If it's not 0, as soon as you're sliding at that point, then we have the principle of maximal dissipation, which means your contact force will be the biggest force possible in the opposite direction of your movement. It will always be the largest force in the cone opposite to the velocity. I promise to not write too low. So moving up the board is kind of a cheat then. Okay, that's the basic principle. Now, Coulomb friction is not complete. You can find cases where this is not enough principles to fully define the forces, and you have to pick one. Okay, here's my favorite example. Right, this is like, classical mechanics is just not good enough. Sort of. I mean, thinking about things as rigid bodies is not good enough. Maybe I should say it's not like the physicists didn't do their job. It's just that the level of modeling of like rigid bodies doesn't capture everything. So take a 4-legged table. Okay, 4 legs are on the ground, right? So if you balance gravity, then you have the sum of those 4 forces have to be equal to the opposite of the gravity. To balance torque, that tells you kind of what at least 3 of the legs have to be doing, right? But actually, it's ambiguous what how it's distributed across those 4. If you had 3-legged table, everything's clean. If you have a 4-legged table, then it's ambiguous. The laws of minimum action and maximum dissipation don't tell you how those forces are distributed. Which is funny, because then, if you push the table, that means that the frictional forces are undefined. So it could go this way, it could go that way, it could go that way, and physics just doesn't tell you. The Coulomb rigid body physics just doesn't tell you which one. You have real tables that have real, so there are, one table leg's a little shorter than the other, or there's microscopic, right? The real table doesn't do that. The real table picks one, but it's at a level of modeling that we are not capturing in this. So what does our solver do? It picks the one in the middle, right? Almost always we're solving optimization problems, so the kind of picking the least norm solution tends to be the right thing. Probably. So I'll say it back to you in my words, though. I think what's going to happen is it's solving an optimization problem, typically in velocities and forces. And it's going to, if there's multiple solutions, it will pick the one that makes the norm of the velocity and forces equal to 0, depending if you're solving it in the primal or in the dual. So its interpretation probably has something like, it probably has an interpretation that you could talk out like that. But I think what's precisely happening is that is in the velocity space probably a minimum norm solution. Okay, so this friction cone idea is key. Like we're going to use this a lot. This is again how do we pick up grasps? We're going to think about putting our friction cones to resist wrenches in the same way that there might be good places to put your friction cone, good amounts to squeeze. That'll change the ability to resist an adversarial wrench. Like the rigid body wrench, not a monkey wrench. Yes, I mean, so basically any force that's inside the friction cone is a possible force. You have additional constraints of the normal force can only be so big, given that it's being powered by gravity here. So the magnitude of that force is determined also by the balance equations. Well, here's a good question. Test your intuition. So in the setting, I have this brick, and I have a ramp. So we said it was mg/2 for the flat case. Is this force bigger? Are they the same? They're not the same. Okay, we got both answers. You have to read the notes to find out. You don't have, there's an asymmetry here, right? That's not pushing like this. Pretty clean in the algebra. Yes?
Can we talk about the polyhedral approximation of the second order function?
Good. Yeah. So I drew this in 2D, and I made it exact in this. Okay. And in 3D, it really is the shape of this ice cream cone. The square root here gives me conic sections that look like this. Okay, but oftentimes for optimization or for faster simulation or something like this, it actually can be useful to approximate this with a polyhedral approximation of the friction cone, where you write this as, because some of these square roots are kind of a nasty thing. So sometimes you'll use a polyhedral approximation of that friction cone. And I could say a lot more, or I don't know how to say a little more than that. But that comes up naturally in a lot of optimization formulations. This would be for instance, if you write a linear complementarity problem, you might have heard of linear complementarity problem, LCP, which is a way to do simulation. The fact that it's a linear complementarity problem is because we made a polyhedral approximation of the cone. If you wanted to do a full second order cone version, then it would be a nonlinear complementarity problem, which is much harder to solve. But that's just bonus. Someone else? Yeah. This is right. So this is a gross summary of the surface materials. The only way that the surface materials come in is by picking mu, right? And so you need to go to a deeper level of detail to get over some of the abnormalities of the model, the insufficiencies of the model. It's also interesting. So if you look in the robot description files, for instance, you can pick you set a mu for each body, but that's weird because mu is really a property of the pair of materials, right? Rubber and glass or whatever, these things are pairs of materials. So there's always a little bit of a hack in the middle where you say, well, I've got a mu of 10 and a mu of 0.3, and I'm going to average them. I'm going to use a parallel resistor theorem or something to put them together, just because it would be a pain to label every pair of materials. But that's what's happening. So you typically put one per body, even though that doesn't really make sense. And there's also you'll see sometimes mu static and mu dynamic, right? So you can have static friction or dynamic friction. It's kind of interesting, but it actually the friction you get once you start sliding tends to be lower than the sticking friction. Okay, so if you make a plot of contact velocity and the total force you'd get out, let's say the normal force, let's see, the friction F tangent normalized by F normal, something like this, okay, then it would, you'll see plots that look like this. They'll have a mu static, where if the velocity is 0, you can get any force in that range. But as soon as you start sliding, that's, I guess, negative mu static, then you'll have a mu dynamic that's actually lower. Dynamic. That's lower. And that's a better model of what's happening in this Coulomb friction. And then you'll see people make, as they make stiff approximations of that sometimes. So you'll see models that look like this, for instance, that are smooth but stiff approximations of that. Okay, so, but oftentimes for first order, just make them equal, you're fine. Yes? Yeah. Because you can satisfy all the equations by putting, like, say, all the force on 3 legs, and the last leg doesn't need to do anything. Or you could put it on the opposite 3 legs, and the first leg doesn't need to do anything. Okay. And then so that's just normal force, let's say. You could satisfy all the torque and Z balance by putting on any 3 legs, for instance. So now when you push, you'll get different forces depending on which of those choices you made, which will possibly cause a moment or not. And they're all admissible by the Coulomb model. That's the extreme. Of course, it would be, you could have any linear combinations of those. That's just, I'm trying to make an extreme case. But that is one solution. But all the equations are also satisfied. Everything that we said that defines physics are also satisfied if you put all the weight on 3 legs. Any 3 legs. And therefore, when you push, you might get no friction on 1 leg, or you might get all the friction, yeah, and which could cause rotation or not. Right? It's kind of annoying. There's other things too that if I was a better chalkboard lecturer, I should learn to do this. The Pan-Lavey paradox, right? So, I can cheat. I can buy something on Amazon to make me a Pan-Lavey paradox guy. Yeah, I don't know how to do it. I won't try. Probably doing it above my head wasn't the best place to start. Okay. So no one liked the fact that I chose the contact points to be at the corners. Let's dig into that a little bit. Okay. I'm glad you didn't like that. I'm glad you called me on that. So, but simulators do that, and simulators have to make a choice. And actually, it's kind of a gross part of simulation. It tends to be a thing that leads to sadness. Like when robots pick up objects and then they go, it tends to be, there's a couple things that can go wrong, but this is one of them, a big one, which is that you have to come up with an algorithm that given, well, so here's the first thing I guess to say is, like, penetration happens. That's the word everybody uses. That sounded out of context, but you will, if you're simulating real systems with numerical algorithms, bodies will overlap. That's called penetration in the computational geometry world, okay? And that happens, and you have to deal with it, okay? So if I have a box on a table, right, then it's sort of easy. I could pick almost any 2 points and find force balance. Of course, I need one to be on at least the right side of the downward force and the left. Okay, but what if I'm on the edge of a table now? Okay, so if I start putting my box kind of on the edge of the table, now it's getting a little bit more subtle, right? The position of this box relative to this box means that probably I need to pick a point right here. You know, and I could pick something else on this side. But what happens if you're like a little bit in the corner, you know, because your simulator took a numerical approximation of the dynamics, and so you're like, I'll exaggerate it. Hopefully it doesn't get this bad in simulation, but you're like this, okay? So where do you put the contact forces? Like simulators have to sort of pick, I'm going to put one here, I'm going to put one here. And it's not that hard for any one image to pick a few contact points. Even in 3D, you get much more complicated geometries intersecting and stuff, but you always look at pairs of bodies, and you could come up with some rubric to pick those points. Here's the hard part. While you're simulating, as the bodies move, you'd really like those points to move smoothly. And it's really hard to find like one algorithm that always finds a consistent set of points, even as the bodies kind of are moving around relative to each other. And if those points jump discontinuously, then your forces can jump discontinuously. And that's when things kind of go surprise. So I actually made some slides about that. I meant to show this before when you asked, but you know, so how do you define the normal vector first in the broader case, even at corners? It turns out that you know, you're always thinking about a normal vector between two frames, okay? And so you take the sign distance between two bodies, which is well defined. We often call it phi. So these two bodies, that would be the sign distance. And the derivative, the gradient of the sign distance is a nice working definition of the normal vector that works even in corners, okay? You can, in general, you just need to be a subgradient of the, you know, of that. Yeah, it's the vector that goes between the 2 points. The distance is a scalar. The gradient is the vector that moves along that. Yeah. And it also it has the interpretation of it being a gradient also works if you're working directly in Q, not just in 3D. So it has a generalized coordinates. And then for the tangential coordinates, you can just pick any basis on the orthogonal plane. And sometimes you pick many of them for the piecewise, for the polyhedral approximation. This would be like the polyhedral approximation does something like that. Okay. So when this is going on, I already showed you that, but just think about this. So if we use that as a heuristic, so it works beautifully when things are out of contact or when they just come into contact. But everything, and I could put up a different proposal, and everything breaks when you start getting into deep penetration. Okay, and here's a picture to make that right. So if you pick the point of maximal penetration, the deepest point in the body, which is a hard computational geometry thing to do, but if you could do that nicely, and then you took the gradient of that as your definition of the normal, then that's going to push you like this, right? That would be my instantaneous choice of a point. Let's just say I'm going to pick only 1 point, just to keep it simple. 1 point, I'm going to try to push in that direction. I'm going to call that my normal, okay? But here's what happens. If you watch that as the bodies overlap, right? Your maximal point gets closer to the other face. So the closest face that would allow you to exit changes discontinuously. Does that make sense? You were closer to the side. You're closer to the side, so you should definitely put your normal force pushing out like that. And then all of a sudden, when you go past the diagonal, you're closer to the top. Boom. Contacts, you know, the simulation has a big discontinuity, and things get bad. Right? So it looks like the gradient of that looks like this. As soon as you cross that boundary, and if you cross it just a little bit, maybe you don't notice. If you cross it a lot, you notice. Okay? So when people are doing point contact, one thing I've learned actually over the years to just, I actually make my contact, you'll notice some of the contact geometry that we use, if you look closely at it, I actually take like a box and I'll just put it, we'll make it a little bit smaller on the inside, call that a box, and then I'll put some extra spheres of radius almost 0 in the corner, just to say like, always put contact points here, please. And then do whatever you want with the rest of it. But at least put contact points here, and that makes things a lot more stable if you're using point contact simulation. Okay. One of the things that was kind of an innovation in Drake in the contact engine was this model called hydroelastic contact, which is the obvious thing in some sense, but it's the thing that making it computationally efficient enough to run all the time at real rates is what was maybe a bigger deal. So now, instead of taking just a point contact or a few points, we take a surface integral across the surface, okay? And even when you're in penetration, we define a pressure field, which defines a surface of sort of a kind of the surface of overlap, and we integrate numerically, we make a new mesh on the fly, and we integrate across that to get nice, smooth contact forces. And that's all happening on every time step, on every geometry pair, and everything like this. So you get these beautiful simulations with nice, smooth red contact vectors, and like I'll show you a couple of examples, okay? So if you do this now, then these are the contact forces that you get out with that extra, extra computational geometry work, and things suddenly get smooth. And that made a big difference in our ability to do sort of sim to real transfer in Drake. Okay, so it's actually a lot of work under there to make that all work, because all of the possible geometry pairs, whether it's a generic mesh or a sphere or whatever, they all have these relatively complicated intersections, and the shape of that intersection depends on the relative stiffness of the bodies. Okay, so there's a lot of things going on behind there. And that's when you get these animations that we like, which is like the dexterous hand picking up the mug, and you'll see the entire contact patch that we render sometimes. And normally you wouldn't see that. That's extra math that we're doing behind the scenes to make that really stable and good. This is all you can turn all this on in MeshCat. In fact, it'll happen automatically. So you'll see any level of these rendering. That's the entire pressure field. When you see red arrows, you're seeing hydroelastic. When you see green arrows, you're seeing the old point contact model. I'm porting the notes. Oops, that was funny. Yeah, I'm actually porting the hydroelastic was a little too slow last year, and it's fast enough this year. So I'm like not even a whole lecture ahead of you, porting the note to use hydroelastic for everything. So you're going to see like a few green vectors, and then if you download it again the next day, it'll be gone. It'll be red. But hopefully you won't have to experience green vectors. Yeah, and like you can watch even like the interaction of the bowl with the table, for instance. You get contact patches that are right around the rim of the bowl. It's a lot of geometry that's happening. It's good. And one of the things that we are proud of, right? So is that like this is another cool example. You can actually mate Legos, and it's just the physics of it will hold it together, right? And the contact forces that come out are just like rock steady and stuff. So most simulators don't have contact forces visualization on by default, because they're like crazy, right? And ours was for a long time too, right? But we have ours enabled by default, just so you're like, hey, you guys should really see these contact forces. Yeah.
Can you control the stiffness like the
Mm-hmm. So there's two different questions there. Can you control the stiffness and damping? Then absolutely. There's a dissipation quantity that they all have proper mechanical units. There's a stiffness that you can set for each body, and then when they overlap, there's a pressure field equation that defines the surface of balance. How does it correspond to real? Right? I think it's intended absolutely to correspond to real, but there's typically some sim to real gaps still. Like if you took exactly the material properties of rubber, you might get something that's a little bit, I would hope it's perfect, But that's the kind of place where you might expect to cheat the numbers a little bit to get a better match. Yeah? You have to say that one again. Sorry. Okay, so the comment was that you have some anisotropic or like some mud or something like that might have different friction properties at different points. So there's no sampling that happens here. It actually is doing the computational geometry of triangular meshes and computing those things and taking integrals cleanly. But if you had a surface that had different friction properties, I think in practice what I would do today, I would just drop a handful of different collision geometries down there that had different coefficients and stuff like this, and approximate it that way. Yeah, we could, of course, generalize it to that, but we haven't put that that level of generalization in there. I think intellectually there's no sampling, right? There, of course, you solve for vertices first, and then you use that to compute the triangulation and stuff like this. But I think the mathematical model that is being achieved by that code is that you're taking an integral over the surface. Mm-hmm. Yes? Yep. Yes, you could. So the question is, could you ever have sort of pass-through effects? So, so Drake supports. And so this is all rigid body, and this is suitable. These are actually compliant rigid body because you're allowed to penetrate a bit. So it's suitable for objects that are mostly keep their shape but could be squishy. But if you had like a really plush toy or something like that, we actually have a soft body simulation for that, which does finite element method. And that could be suitable for things like cloth or something like that, but we actually don't advertise cloth support yet because exactly because of these pass-through events. And we know how to the simulation community knows how to do that, but you just have to do extra logic to prevent pass-through, because if your normal suddenly pops out the other side, then that's can be bad. So this one, I don't think it would be devastating. If you had enough mass of your pepper still on the first side, then it would probably be almost unnoticeable. So we don't feel like a sucking sound if you happen to hit the table or anything like that. But you could have more dramatic events where you actually just pass through. If your simulation time step was too big, you would just enter, or your stiffness was too low. Yes. We summarize the integral of the pressure field in a wrench. That's one of the reasons. So that's kind of why I showed this partly, is that it's beautiful to say that the integral over that, it gives you a total wrench. Mm-hmm. Good, I'm going to stop there. Think about your project groups, think about your projects, ask us questions, and we'll see you Thursday.